Welcome all. So we're going to be talking in these next few segments about the quantum mechanical nature of the atom and how that actually explains a lot of what we observe in the periodic table and really fundamentally explains all the chemical reactivity we see. So the learning objectives for this segment: be able to convert between wavelength, frequency, and energy, be able to explain situations where light behaves like a particle, and explain situations where light behaves like a wave. So what's the context for all of this? So let's think back to the periodic table. Elements are organized in vertical columns in the periodic table because those in the same group have similar chemical properties. They behave in similar ways. So the question is, how can we explain this geometry? And it turns out that the quantum mechanics of the atom provides the direct answer. They explain why particular elements react in similar ways and why they're different, why those differences occur as well. So bear with me for a little bit, because it's going to take a day or two to get to the point where we can explain this in terms of quantum mechanics. So first, before we get to atoms, we need to understand the nature of light in order to understand atoms, because that's how scientifically we figured out atoms behave the way they did, by shining light at them and seeing how they changed. So all of light, electromagnetic radiation, can be described by wavelengths. It's essentially a wave in the electromagnetic field. And the light we usually perceive with our eyes, the part of the electromagnetic spectrum that we perceive with our eyes, is really a pretty narrow range between about 380 nanometers, or 3.8 times 10 to the minus 7th meters, and about 780 nanometers, 7.8 times 10 to the minus 7 meters. There's a lot larger, a lot bigger scale than this. Radio waves can be on the scale of meters or even longer. Infrared are somewhat longer than what we see in visible. If you get a little bit longer than red wavelengths, you get visible light. And on the other hand, ultraviolet light has shorter wavelengths than what we can see. X-rays and gamma rays, which get to be very energetic, have much shorter wavelengths. So there's really a huge spectrum, and all of these types of light interact differently with matter because of their characteristic sizes and energies. The differences in their wavelengths and energies determine how they interact with matter. Okay. So it's interesting that everything we see with our eyes is only a small part. It turns out to be enough in many cases, because most things that throw off light over a wide range of wavelengths. And there's actually a reason that visible light is what we see, and it turns out that the chemistry of the molecules involved in photoreceptors, there's only a certain range of wavelengths that are easily accessible through changes in the chemistry of the photoreceptors in the eye. And so those are the ones that we can pick up on. Obviously, different animals with different photoreceptors can expand the range down a little bit or up a little bit and see in the infrared and UV, but not that much further, because just the limitations of energies accessible by chemistry. So light has wave and particle-like properties. This is the first thing we have to understand. In many ways, light behaves as classical waves of electromagnetic radiation. When I say classical waves, meaning you can write them down as the function being just a sum of sines and cosines. But then also, light occasionally behaves as discrete packets of energy. That is a localized chunk of energy, not described as a wave like a water wave. And so that can be very confusing. And even in this class, we're not going to get into all the situations where it behaves like a packet, all the situations where it behaves like electromagnetic radiation. We're going to look at those phenomena in particular areas that are important to chemistry and their interaction with atoms. Okay, so let's get the terminology and the numbers right. It's not very hard, but it can be confusing, because there's a lot of things where you have to remember whether it's the relationship is proportional or proportional to 1 over the thing, and that can be a big pain. So we have the mathematical function of a wave, and some of the terminology we use. We have the peak, where the magnitude of the wave gets the largest, and the trough, where it gets the smallest, just as you'd see in waves in the ocean. And looking at how do we measure the size of this, there's really two ways of measuring size. One is measuring the distance between successive wave peaks. If you take a snapshot of it in time and you say, if I have these peaks, how long a distance is it between the peaks? And that's the wavelength, which makes sense. It's the length of the wave. The frequency is the number of wave peaks that pass a given point per unit time. So if you have a wave moving over time and you have a stopwatch, you start it and you count how many peaks occur in a given amount of time, and that is the frequency that the wave peaks pass by. And the frequency and wavelength are very intimately related, as we'll see. If you know one, you almost know the other. Amplitude is another measurement for waves that just has to do with how high the height is, and it's completely independent of the wavelength and the frequency. You can have long wavelength waves with high amplitude or with low amplitude. Those are completely independent things. Wavelength and frequency are related though. So looking at characteristic wavelengths, so violet light would have about a 400 nanometer wavelength, infrared radiation about an 800 nanometer wavelength. And an interesting thing that we're going to talk about in relationship to atoms is, the size of atoms are, less than 1 nanometer. So wavelength of light is actually much bigger than an atom. So it's sort of interesting to think about absorption of something that has a longer wavelength than the size of the thing that's absorbing it, which is something that leads to some of the confusions, leads to some of the weird math. Okay, so again, what we perceive as different kinds of electromagnetic energy are waves with different wavelengths and frequencies. And here is the fundamental relationship that's important, is that the wavelength times the frequency is equal to the speed of the wave. In this case, if it's electromagnetic radiation, the speed is always the speed of light, no matter whether it's violet light, infrared radiation, gamma radiation, all of them have exactly the same speed. And so if you know the frequency and you know the speed of the wave, then you know the wavelength. So for light, we always know the speed. If it's the speed of a wave in water, then of course you need to, that is not the speed of light. You need to know what the speed of that is, or the speed in sound. But this relationship holds for any type of wave. Absolutely any type of wave. This is always true. With electromagnetic light, then you always know what C is. And the way you can see this is you can write this as the frequency is the number of waves per unit time, and the length and the wavelength is the length per wave. So if you do that, then you notice that waves cancel out and you get length over time, which is a speed. So that's one way to remember that, that the frequency times the wavelength has to equal the speed of the wave. If you know how long it is between peaks, and you know how many peaks are passing per amount of time, then you know the amount of length that's passing per unit time, you know the speed. Okay, so generally, if you just remember this equation, one can figure out most of the other relationships. So that's the one to always keep in mind, always remember. Frequency times wavelength equals the speed. So let's make this quantitative. The blue glow given off by Mercury street lamps has a main frequency of 6.88 times 10 to the 14th inverse seconds, or hertz. So inverse time is the unit of frequency. Inverse seconds is the name of hertz. What is the wavelength of this light in nanometers? Okay, so let's jump in and start doing the calculation. So what's the equation we want to be working with? Same one, we're all, the one we said was the key. Frequency times wavelength. So that wavelength is the lambda here for length equals C. Great, so what do we want? We're given the frequency and we want to know the wavelength. So we just need to rearrange. Wavelength equals speed of light over frequency. Here I'm using nu, that's the most, it's actually not a V, it's a nu, which is the most common letter used for frequency, the Greek letter. So we have 3.00 times 10 to the 8th meters per second, the speed of light, divided by 6.88 times 10 to the 14th inverse seconds, that's hertz. So the inverse seconds cancel on the top and bottom, and we get 4.36 times 10 to the minus 7th meters. And if we then note that 10 to the 9th nanometers are equal to 1 meter, that cancels, and we get 436 nanometers, which puts us squarely right here. Yeah, that is indeed a bluish glow. So those are the, if we remember that frequency time wavelength equals speed, then we're set for a lot of